In the last two sections, we've calculated or we've studied magnetic fields from a current loop, and we calculated the magnetic field from the current loop using the one-dimensional form of the Biot-Savart law. Now, one of the points that I made when we were discussing this law was that it was a special case of the three-dimensional form of the equation. So really what we'd like to do is we'd like to study this three-dimensional form, and we'd like to formally be able to reproduce the one-dimensional form, or perhaps more importantly, we'd like to be able to incorporate one-dimensional problems within that three-dimensional formalism. Similarly, we'd like to be able to incorporate two-dimensional problems where instead of having a line of current, we might have a sheet of current. We'd like to deal with them all under the same formalism. And we're going to find that the delta function is a very useful tool for achieving this goal. So before we go any further, let's consider the following situation. Imagine I had a current in a straight wire, we'll say a current I, and the wire was straight along the z-axis, in the following way. So let's put the z-axis here. Okay, so the current is along the z-axis, and if we were going to use the Biot-Savart law, of course, we'd be tempted just to do it in one dimension in the following way. Okay, so we could write such an integral down in one dimension, or alternatively, we could notice that if we were to write down the current density in terms of delta functions, we could incorporate it in our three-dimensional formalism. So let's consider the following equation. Okay, if we were to take this equation and put it in our three-dimensional formula, you'll notice the following. Let's just do it. Let's just map it out and see how it goes, and you can try it on your own. The two delta functions in delta x and delta function in delta y are going to remove the two integrals over dx prime and dy prime. Pardon me, I should be very clear about my primed and unprimed indices here. Okay, so now the two integrals over x prime and y prime, which will be as part of this volume integral, these are going to be removed by the presence of delta x prime, delta y prime. You'll notice that we'll be left with an integral over dz prime only. There it is. Furthermore, it will be proportional to the term I z hat. So using this form for the current density in our three-dimensional equation here is going to reproduce our one-dimensional form for the equation. This is really very nice because it gives us a nice way to generalize this three-dimensional result. Let's consider a two-dimensional result, and we'll see that delta functions are similarly useful in that situation. Okay, so what I've drawn here is a two-dimensional sheet of current. So the idea is that it's infinitesimally thick in the z direction, but we have current flowing in this sheet, and furthermore that current can be a function of position. And I've labelled that current as K, which is the two-dimensional analogue, if you like, of the current density J. K has the units amps per meter. So let's put that here. And the idea is the following, that if let's say K were a constant, were a constant, so it was k amps per meter, and independent of location in the two-dimensional plane. If I wanted to know how much current was flowing across a particular uh, line segment perpendicular to k, I would just say that it is k times the length of that line. K times the length has units of amps. If, on the other hand, k were a function of position, I would have to integrate it along this line to get the total current crossing this line. So in 3 dimensions, we think about a current density with amps per square meter, and we integrate it over an area to get a current. In 2 dimensions, we have k being a quantity with units amps per linear meter, and we integrate it over a line to get the current crossing that line. Okay, so the question then would become the following. How do I write k in this situation down in terms of the three-dimensional current density J? So let's consider for the moment that k is indeed constant, and furthermore it is in the y hat direction according to the set of axes that I've drawn here. So we're going to deal with a case where k is equal to k y hat. Well, in this case, I could write that in the following way. I could write the current density J is equal to k delta z y hat. And if we look at this formula, we'll see that it does all the necessary things. K is 0 everywhere except at z equals 0. That is in the xy plane. So I put this in the xy plane. I should be clear about that. J is in the y hat direction. And furthermore, if I were to integrate J over a small volume that included this sheet, I would indeed get the right current. And you should try that. I suggest that you try precisely that calculation just to see how that comes out. Alright, so let's, well, maybe we'll do it on the next page. Let's see how that goes. If I had if I wanted to calculate the magnetic field from this current density, then I would get the following formula. Okay, so there is our formula now for the two-dimensional situation, the particular one that we studied, but you'll notice that we were able to use our three-dimensional result and our understanding of delta functions to adapt our three-dimensional result to what is actually a purely two-dimensional situation.